Well, thank you very much for that introduction. I can see why you're a champion Toastmaster. Perhaps I'll give a few more lessons in my talk, which I've slightly changed the title of, since I understand there are many young people in the audience, and I thought it would be more interesting to give a talk entitled My Life in Physics, From Quarks to Strings. As Sri said, I got started in physics at a very early age, maybe 13 or so, by reading popular science books. It is true that I was living at that point in Jerusalem where there was no TV and the internet had not been invented. Those are distractions, can be, but they're also marvelous resources. Everything is now available to all of you with the push of a finger if you know where to look. But at the time, you had to read books. And I, as a young adolescent, started to read these marvelous books on science written by some of the greatest scientists of the early 20th century. George Gamow, whose series of books is still worth reading. Arthur Eddington, who wrote about the growing knowledge of the universe and astronomy. My favorite was Albert Einstein. And this book, called The Evolution of Physics, is still available, and I highly recommend it to people who want an introduction to the basic concepts of physics. Einstein was my hero in a way, a godlike figure who achieved miracles with it, working only with his brain. And since I like doing mathematics and puzzles, I felt it would be a lot of fun to spend one's life solving puzzles, but not puzzles invented by a puzzle maker, but puzzles that are presented by nature itself. To use one's mind to try to understand how nature works. And Einstein exemplified that achievement, in which, by the way, we celebrate this year, or actually about a month ago, is the 100th anniversary of Einstein's equations that describe his theory of gravity, which has stood the test of time and remains a subject of current research. My talk today, later today, will be on how Einstein's visions still guide us and how they relate to current problems. And Einstein said in one of his papers that what the role of a physicist like him, a theoretical physicist who works with pencil and paper and ideas and formulas and equations, was. He said the supreme test of the physicist is to arrive at those universal elementary laws of nature from which the cosmos can be built up by pure deduction. That's a very ambitious, arrogant statement. But to a young person like me at the time, very attractive. So I decided very early, maybe 13, 14, that I was going to become a theoretical physicist. I didn't know what that really meant or what theoretical physicists really do, but that was the goal. And then it's easy once you make such a decision. You go to school, you study hard, you learn the basics of physics, you go to the university, and at some point you are ready to engage in research of your own at the frontiers of knowledge. Now, At the time, the frontiers of knowledge were mainly concerned with what is called elementary particle physics, namely the discovery and understanding of the basic constituents of matter, the basic building blocks of all matter, the atoms of matter, and the forces that act on them and create the structures that we observe. Well, after finishing my undergraduate studies, I went to Berkeley, California, which was at the time the center of elementary particle physics. Today, the biggest accelerators are in Geneva at CERN, but back then, in the 60s, the biggest accelerator was at Berkeley. There it is. By today's standards, it's very small. It's 1,000 times lower energy, or actually 10,000 times smaller than today's accelerators. But at that time, it was the center of experimental particle physics. And the main question that people were trying to understand was, what goes on inside the nucleus of atoms? What is the nature of the nuclear force? Now, this study of elementary particles, the nucleus, started also about 100 years ago with the discovery by Ernest Rutherford in 1911 of the nucleus. What Rutherford did was try to understand the structure of the atom. By that time, people were pretty convinced that matter was made of atoms, and atoms contained electrons, negatively charged point-like particles that J.J. Thomson had discovered in 1890-something. But that's all they knew about the atom. Rutherford wanted to look inside the atom, but the microscopes that one has are not good enough today, beginning to be good enough, but at that time not good enough to look inside the atom. So he did something different. He took alpha particles. Those are actually nuclei of helium emitted in radioactive substances. Rutherford by then had won a Nobel Prize in chemistry for his discoveries of radioactivity. So radioactive atoms emit alpha particles, and these particles have charge, and he didn't know what they were, but he used them, shot them at a thin foil of gold here, in order to see how those alpha particles would deviate, would scatter off the atoms of gold. Try to use those projectiles of alpha particles to get inside the gold atom and see what was there. And he had a postdoctoral fellow called Geiger of the Geiger counter, and a undergraduate research assistant called Marsden, and they would sit in a dark room for hours until their eyes were accustomed to the dark, and then they would observe the scintillation of the scattered alpha particles on a fluorescent screen. They would measure how many particles came out at different angles, how they were scattered. Some would scatter very little, some would come almost back at you. And from that you can deduce what is the structure of the thing that scatters them, which should be, he concluded, a very, very small nucleus, he called it, where all the positive charge of the atom, electric charge of the atom is located, and most of its mass. That was the discovery of the nucleus of atoms. The nucleus of atoms is very small. An atom is 100,000 times bigger than the size of the nucleus. So it's very hard to probe inside the nucleus, and that was the subject, has been the subject of experimental discovery and exploration ever since. And we use the same method that Rutherford invented 100 years ago today. What is that method? Well, one way of describing that method is, let's assume you have two Swiss watches. And to understand what happens, how they're made, what you do is collide them. That was kind of cute. Let's do it again. Oops. So you want to understand what these watches are made of and how they work. What we do in elementary particle physics, or my experimental friends do, is take these watches, smash them together, and take a picture of what happens right after the collision. Then we look at the picture and try to identify what the watch is made of and how it works. Now, you might say that's a pretty stupid way to figure out how a watch works. Why not just open it and look? The trouble is, you can't just open the nucleus or open a proton and look. This is the only way we have so far, just about the only way we know how to study the inside of the atom, inside of the nucleus, the inside of protons and neutrons that make up the nucleus, the inside of the quarks that make up the proton, the inside of the quarks, if there is an inside. And that method has been pursued now for 100 years. Of course, in my time when I came to Berkeley, the picture, this is actually cosmic rays, which also accelerate particles in the magnetic fields of the galaxy, and they collide on Earth. And these pictures are taken in a cloud chamber of various collisions and particles coming out, and you, in a magnetic field, try to measure the trajectories of the particles, identify them, and when I came to Berkeley at that time, the experimentalists were making lots of discoveries in an exciting time in elementary particle physics. But the theory was useless. The theorists had really no understanding of what was going on. They were not very successful in applying the quantum theory of fields to this problem. In fact, at that time, or some years before, Freeman Dyson, who had contributed to the quantum theory of electrodynamics, of electricity and magnetism, said the correct theory of the nuclear force will not be found in the next 100 years. So he turned out to be wrong by 87 years. And I'll tell you a bit about that story. Today we have much bigger collisions. We don't just take particles and smash them against inert matter. We take two particles, accelerate them both to very high energies and smash them together. And we take pictures with very sophisticated detectors, not graduate students seated in a dark room. The pictures look something like this. This is a picture of one of the billions of events that are produced at the Large Hadron Collider at CERN. Here's where the collision takes place. As you can see, lots of particles are produced. This is the picture. You have to look at this picture and try to figure out what's going on inside the proton at very short distances, very high energy. It's not easy. Back in my day, experimentalists were making rapid progress. This is a history line of the discovery of elementary particles. The electron was discovered actually back, just before the end of the 19th century. The proton, as I said, the nucleus was discovered here, and it was realized that it contained protons, the nucleus of hydrogen. By this time, we had a theory of atoms that quantum mechanics gave us. And the neutron was discovered, it took another 10, 12 years to discover the neutron, the other particle that sits within the nuclei of the atoms that you're made of. Shortly after, the positron, which is the antiparticle of the electron, was predicted by the theorist Dirac on the basis of relativity and quantum mechanics, and discovered. The second family of leptons heard this beautiful song, dance about the electron and its sisters, the muon. Sisters that join the family of leptons. And then, after the war, a lot of research money went into particle physics, and people started discovering particles all the time. When I came to Berkeley, experimentalists were discovering a new particle every other week. It was very exciting. And hundreds of new particles, which were similar to the proton and neutron, strongly interacting. They had this strong nuclear force, very similar to the proton and neutron, and no one really understood how it worked at all. Which, for a young theorist like me, was great. Lesson number 6. In science, probably the same applies to every facet of life, business, whatever. Always look for the field or the question or the research direction which is the most challenging, where everyone else has failed, and where no one is working. Well, not no one is working. Don't just do the easy stuff. So I was particularly challenged by the fact that really there was no theoretical understanding. Now, and by that time, people were doing very high energy experiments of this type, colliding particles together to see what they were made out of, if anything. Now, by the end of the 1960s, it appeared mathematically that many of the patterns of these particles could be explained if you assumed that protons and neutrons were made out of a kind of particle that no one had ever seen, a quark. Quarks have fractional electric charge, according to this mathematical description, but no one had ever seen any piece of matter with a fraction of the electric charge of the electron. Quarks were supposed to have charge 1/3 or 2/3 or minus 1/3 or minus 2/3. No one had ever seen that. So it seemed rather strange and somewhat a mathematical abstraction. So, according to this mathematics, the proton was made out of two kinds of quarks. We call them today flavors, up and down. And the proton was made out of two up quarks and a down quark. And if you flip the up quark to the down quark, you got the neutron. And other combinations of up-down quarks and other kinds of quarks that seem to be necessary, called originally strange quarks, since they were strange, could produce the pattern of the various particles that had been discovered. To make this at all sensible, one also had to do something else and assume that each of these quarks, the up, down, and strange quark, came in 3 different colors, 3 different kinds. There wasn't just one up quark, there were 3 up quarks, all the same except for the label, up, red, blue, green. We call them